characteristics of the diode, you see, diode is inherently a nonlinear electronic circuit device in which the IV characteristics are it's an exponential in the forward bias regions where you apply the external bias such that the VD positive terminal is connected to the P-type region and the negative terminal is connected to the N-type region. So the current that you derive once VD is sufficiently large, is greater than the barrier potential, you have an exponential increase in the current of the diode. So it's a nonlinear device, okay? And in the reverse biased, when VD is less than 0, or in the reverse biased, external bias, when the external bias is such that the N-type region and the negative lie to the positive region, you don't have any significant current. It's in order of maximum in order of picoamps or 10 to the power minus 18 amp for a typical silicon PN junction. So, but then it turns out that there are some secondary effects. You see, temperature has a very strong dependence on this reverse saturation current IS, which in turns depend on the intrinsic carrier concentrations. I mean, if you go on increasing the temperature, the reverse saturation current is increasing, and for a silicon single crystal silicon lattice, it doubles after every 5 degrees centigrade. I mean, since you are giving more energy, the electrons, they might break free from the covalent bonds and increase the carrier concentration. So as the intrinsic carrier concentration increases in the single crystal silicon lattice, the reverse saturation current increases. Okay, and it turns out that materials like germanium, which has a lower band gap between the valence and conduction bands, germanium concentration increases more rapidly as compared to silicon. Okay, so germanium in that sense is not a practical material for operating diode in reverse bias regions. Okay, so one parameter is the reverse saturation current, and if you recall the relationship that we discussed last time for the diode current was in terms of reverse saturation current IS, and then we have an exponential, and that was in terms of we had an ideality factor. So okay, we have VD, and then there is N minus 1, and let's see if we are missing something over here. Yes, we have VT, the thermal voltage as well. Okay, so if you look at this expression, IS has a temperature dependence. Okay, as the temperature increases, there's more free carrier concentration. Okay, the other parameter that depends on temperature in this relationship is VT, and this VT is the thermal voltage. And if you remember, VT is KT by Q, where Q is the fundamental charge. So this is your thermal voltage, and at room temperature, this is approximately equal to 26 millivolts. Okay, but owing to its dependence on the temperature, this parameter is also variable. Okay, so one is the reverse saturation current, and the other is the thermal voltage. Both are the function of temperatures. So that in turns it depends that since they are dependent on temperature, your diode current ID is also temperature dependent. It's also a function of temperature then. So the diode characteristics, they vary with temperature. The temperature related variations in the power bias characteristics is shown in 120. This is figure 120. What it shows is that, okay, for a certain current requirement, let's say diode current ID naught or ID 1, whatever you say. So if the temperature is varying, the forward bias external bias requirements to generate the same current decreases. Okay, so as the temperature is increasing, you see, for example, this one is VD1. Okay, let's call this V1. Okay, so the first curve is for V1, the second is V2, and then V3. So in order to generate the same current, in order to generate the same diode current, if the temperature is increasing, T2 is greater than T1, which is greater than T0. So for the highest temperature T2, the voltage is the minimum. Okay, I mean, the voltage requirements to produce the same current becomes less as the temperature increases. So forward bias PN junction characteristics are shown versus temperature, and the required diode voltage to produce a given current decreases with an increase in temperature. Okay, and that is primarily due to these two parameters, the reverse saturation current and the thermal voltage, which are dependent on temperature. Therefore, you have the dependence of current, diode current on the temperature. Then, okay. So the requirements for the forward bias VD voltage decreases to generate the same current for higher temperatures. Okay, this is what is being shown in this figure. So you see, for a given current, the required forward bias voltage decreases as temperature increases, and for typical silicon diodes, the change is about 2 millivolts per degree centigrade. So about 2 millivolt reduction is there in the forward bias voltage VD for every increase in temperature degree centigrade. Okay. Now the parameter Is is a function of intrinsic carrier concentration, Ni, which in turn is strongly dependent on temperature. Consequently, the value of Is approximately doubles for every 5 degree centigrade temperature rise. The actual reverse bias diode current, as a general rule, doubles for every 10 degree centigrade temperature. So if you have a real silicon reverse bias diode, in practice, for every 10 degree rise, the reverse saturation current increases. Okay, so it might not be a very good voltage controlled switch then, because you understand that if you reverse bias the polarity, the reverse saturation current has to be negligible. Okay, but if it is increasing and if the carrier concentration is increasing, then it makes the device less of less practical importance. So as an example of the importance of this effect, the relative value of the intrinsic carrier concentration in germanium is larger as compared to silicon, resulting in a large reverse saturation current on germanium-based diodes. So this increase in the reverse current with increase in temperature makes germanium diode highly impractical for most circuit applications, because in reverse bias we are going to have a very significant current because of increasing reverse saturation current as temperature increases. So germanium diodes in reverse bias are not very practical and useful as compared to silicon diodes. Okay, so because if you see, if you go down the group 4 table, and if the difference between valence and conductance band is decreasing with very small increase in temperature, the Ni, because Ni is increasing a lot, so you cannot go down the group 4 table and have those diodes operating in the reverse bias regions because of the temperature effects. Is is going to increase a lot, and you might burn out the electronics. Okay, you might not burn out; it would be an exaggeration, but Is will be significant. Okay, as compared to silicon diodes. So that's all on the temperature.